and you have space right beside this. A key thing in a polynomial function is this idea of a leading coefficient. So I'm going to highlight that. And we're going to just make a note about odd functions, which means that the highest exponent or the highest degree is odd. So these are lines, these are x cubed graphs, x to the 5, x to the 7, x to the 9, and so on. If the highest degree is odd, then we can make the following note, that the end behavior acts like lines. And what that means is if you have, for example, a y equals a negative 3x to the 7 graph plus dot, dot, dot. And it doesn't matter what happens after that. You know it's an odd one from the x to the 7. And having a negative coefficient, you just think about what would happen if I had a line with a negative slope. It would go down from left to right, meaning that there would be an arrowhead in the top left-hand corner and an arrowhead in the bottom right-hand corner. This will be the same for this negative x to the 7. And if you had an odd one with a positive leading coefficient, then you would think, well, what happens to a line with a positive slope? It goes up from left to right. So the end behavior of this 2x to the 5 graph would start bottom left and end top right. And this is true for all odd functions. If you have an even function, which means that your leading, or highest degree, sorry, not leading coefficient, the highest degree is even, then the end behavior acts the same way when we did parabolas. So for example, if you had a 3x to the 4 graph, you think of a parabola with a positive leading coefficient would open up, and so your end behavior of a 3x to the 4 graph will be up in both directions. And if you had a negative leading coefficient, like negative 2x to the 6th, it's even. Think of a parabola opening down, and its end behavior would match with this.
The highest degree is the thing, right?
The highest exponent.
Exponent, okay.
Yeah, when we say highest degree, then that's like a highest exponent.
And it's even and odd total. You know.
Yeah, because 2, 4, 6, that's even numbers. Odd, 1, 3, 5, 7. Okay. So they have in the chart below, they're like, all right, well, if you have a line, is it any surprise that the line acts like a line? If you had a positive slope, its end behavior would go up from left to right. A negative slope, it would go down from left to right. And if you had a parabola, the first even function, well, if it was a positive leading coefficient, it opens up. A negative leading coefficient, it opens down.
Could you just show the other picture again?
Yes.
What's the drink that you keep in that small?
It is just a tea called yerba mate from South America. And you traditionally, I guess I could pause the. All right, so we had the parabola Parabolas act like parabolas, but then once we get to the new ones that we're gonna have to graph, if you have an x cubed graph, highest degree is the power of 3, then you think it's going to act like a
Hi,
line.
sorry to interrupt. Can Talia come down to the office with her belongings, please?
All right.
You.
Sneaky early trick-or-treating, getting out there earlier for the rest. So if it acts like a line, notice how it starts down here and ends up here. And if the leading coefficient was negative, think about a line with a negative slope, and sure enough, it starts up here and ends down there. Same thing happens with a quartic, power of 4. It's an even function. So we think of parabolas, and since the leading coefficient is positive, you think of a parabola with a positive leading coefficient, and this end behavior opens up. If the leading coefficient was negative, think of a parabola opening down, and sure enough, this one's end behavior opens down. And finally, they have an x to the 5 graph. It's odd, so think of lines, positive leading coefficient, start down here, end up here, and negative, start up there, and down there. Notice there can be a lot of crazy stuff or relatively little crazy stuff happening in between. We'll be able to figure out a little bit of that, not necessarily all of it, but a little bit of it, setting us up for next year, calculus figures out the rest. So let's go to example, before we go to example 1. Now, the textbook has written this out nicely in words, but I think you can figure this out a lot easier just by thinking of lines. There we go. There's your end behavior. If you have an odd function, positive, it has to end down here and end up there. If it's negative, right? Now they've written it out in words. As x goes to negative infinity, so you're going to the left, the graph falls to the left. And as x goes to positive infinity, the graph rises to the right. I think the diagram says exactly that, and it makes a lot more sense. Same thing, there's words for the positive one. And then when you get to even degree, just think of parabolas. There's our end behavior. As x goes to negative 50, the graph rises to the left, and as x goes to positive infinity, the graph rises to the right. Similarly, here's a negative parabola, there's your end behavior. And they have the words to describe. So if we go to example 1, and we're asked to graph each of these, the first thing you would notice is that the highest degree, or the highest exponent, is a 3. It's odd. The leading coefficient is positive. So you think of a positive line, and you know that this is your end behavior. So we're going to try to graph this. But right now, all we know is where the graph ends in both directions. In order to graph the rest, right now, the only thing we have as a strategy is we find some points. Like I could plug in 0 and get 0. So I know I have this point. I could plug in 1 and get negative 2. And the more points I plug in, the more accurate I would get as a graph. So I have 3 points so far. I could probably plug in 2, and I could plug in 4, and I could plug in negative 1, and get more points. And as I get more points, I think, well, I know it has to end down here, and end up there. I get an idea of what my graph looks like. Also notice that this no horizontal line goes through the graph, more than 3 times because it's an x cubed graph. X to the 4 graph, that's negative. So I would know that my end behavior looks like this. I would definitely plug in 0 and get my y-intercept at 3. And again, as you plug in more and more points, you would get an idea of what this graph looks like. So we could plug in 1, -1, -7, -9, -17 plus 3. 1 would be -14. What happens if you plug in -1? You would get -1 plus 6 is 5, minus 9, -4, plus 3, -1. And I'm doing the mental math very quickly. And I don't really care if we get some of these wrong at this point. It's just the idea. You could keep plugging in points. The more points that you plug in, I don't know. I think this one might look something like that. I don't know. You can't really get a sense of what it looks like unless you do a lot of points. So, table of values, very powerful for graphing. In fact, that's what your calculator does. That's what AI does. It's like, they are good at doing millions of calculations very quickly. So they just go plot, plot a bunch of points, and then they got their graph. Humans are not good at doing millions of calculations quickly. So, although this is a great method, it's tedious, and we want to find something better. Okay? But never forget the tedious method, because there's been some provincial exams where, like some questions in particular, every single student who tried to do a shortcut method got it wrong. And the students were like, you know what, I'm just going to go back to the basics and do a table of values, were the ones that got the question wrong. So sometimes just getting the regular points is the best strategy. All right, questions for practice on this one are 5, 6, and 8.